So I already mentioned that sequential consistency can be viewed as overly restrictive for some situations. So what other options are there? So right now we're going to look at few other memory models that are what's called weaker memory models than sequential consistency. The first one we're going to look at is called total store ordering, which was introduced by Sindhu. So total store ordering sort of half implements sequential consistency. I'm trying to show in this picture what's going on. It makes a global order between all the stores, but no order between the loads. So the loads, so there is, as shown in this picture here, there is this selection mechanism can choose store from one thread at a time and put them in the global order. So everybody's going to see that order that has been performed. But there is no requirement that you have to put all your stores in the global order before you put your loads. Instead, you have this little buffering capability we're going to talk about in a little while. So a store can actually sit and get ripe here in this buffer until the memory system feels like it's time to put it in global order when it's selected by this red mechanism, and then it will be put in the global store order of this memory system. So programmer's intuition is almost maintained here because we have an order between all the stores performed in the system. But even this can be sometimes be viewed as unnecessarily restrictive. We're going to look at some even weaker models after this. So this is an example how you could implement total store order. So here you may remember the store buffer from the cache lectures. If you have a store buffer in your system, you cannot implement anything stronger than total store order. So as you may recall, when you perform a store, it's not performed in memory right away. It can sit and wait in the store buffer, working its way up here in this FIFO, and it gets to the top of the buffer, and the memory system, the selection mechanism in red from previous slide, decides to choose it to be performed and put in the global store order. Meanwhile, its loads can bypass and go straight out and read and write memory, and that's important because loads often return data values in registers, and those values may be necessary to have those values in the register. Otherwise, you may have to stall the pipeline. So that's why we bypass the loads over the stores. But just to make sure we not confuse the programmers all too much, we make sure that if there is a store that this thread has performed sitting in this store buffer, is a store to a specific address, and then you perform a load to the same address. These comparators make sure that we catch that, and we make sure that this new value, which is soon to be written in the global memory model, will be returned by that load. So a thread may see its own stores put in the global order. You see its own stores before others we're going to see their stores before they are being put in the global order. So this is TSO, and we're going to go back and look at the programming examples we looked at before and see if they still make sense when we execute those examples under this slightly more relaxed memory model. So first, the flag synchronization. So that was the dependence we had in the flag synchronization. First, A is written by a thread, then flag is written by a thread, and then another thread first sees flag, and after that it tries to read the value of A. So I'm going to pose the same question to you. Given total store order, what value will be printed? So given total store order, that means that this store must be put in global order between the store to the flag. That means if anybody has observed that the store to the flag has happened, and that observation we make right here, they might also already have observed that A has happened. So yes, this flag synchronization works as it's written here. So the correct value is 1. So causality, that's slightly more complicated, and let's remind ourselves what's going on here. It's 3 threads involved. One is writing. Its write is observed by somebody else. After that, it performs a write. which is observed by somebody else, and after that it tries to read the value that was written way up here. So I asked the same question, given total store order, what will get printed? Turns out that also this example holds. Since this store up here must be put in global order before it can be watched by this load operation here, that means that its store must also be put in global order after the store to A. That means that A happened before B, so if you have seen that B has happened, then you must also have seen that A has happened. So that still holds. So what about Dekker's algorithm? Will that still hold? So let me so given total store order, is it possible that both thread wins? And the answer that Dekker wants is the no answer. Another way to phrase that is to ask, does this write up here become globally visible, which means seen by the other side, before this read of B is performed? So the answer is that Dekker's algorithms will break under total store order. So it's the yes answer. It's possible that both A and B win. And think about this as, think about the store buffer example. So this thread to the left puts its store to A in the store buffer. Then it bypasses the store buffer with this load and goes out and reads the value of B out there. Meanwhile, the other side may already have put a store to B equals 1 in the store buffer, and it can bypass that store, go out in the world, and it can draw the conclusion that A is still equal to 0. So it's still possible to write code that will break under total store order. So how can you fix this? Well, you can actually make Dekker's algorithm work, but you have to ask the programmer to do some of the heavy lifting. What you have to do is to ask the programmer to tell exactly when order matters. And more specifically, if we want a load to be globally ordered before, if we want a store to become globally ordered before we perform a new load operation, we have to tell the hardware that this is what we want. And we do that by putting in a memory barrier instruction. This is typically not included in high-level languages. You have to go down and do insert some assembler code in your programs, or have some macro that will do that for you. But it's for the total store order, it's exactly this situation. You have performed the store operation, you want it to become globally visible before you do a load. So how can you implement that? So when these hardware people get this message, this instruction is executed, says you have to impose ordering, all we have to do is to make sure that the store buffer is flushed. We cannot let this load start until the store buffer for this thread is empty. When it is empty, then it's when we have implemented the semantics of the memory barrier, and Dekker's algorithm would actually work. There are even weaker memory models. So there is a memory model by Michel Dubois called weak consistency, or weak memory model. And there is one called the release consistency by Kouroush Karakolu. And these models and some other weaker models as well what they have in common is that it's pretty much no ordering guaranteed whatsoever. So all the threads can read and write in whatever order they want out to the shared memory. So we cannot establish a global order. And when we want there to be a global order established, so the flag synchronization doesn't work. If a thread performs a store followed by a different store, we cannot guarantee that those stores will actually be performed in exactly that order by any other thread. Causal correctness doesn't work either, and of course Dekker wouldn't work under that model. So we have to rely even more heavily on the programmer to tell us when order matters. So the programmer will have to insert more memory barriers. But the payback is that we could potentially implement this kind of memory model with a higher performance, because we can do more things in parallel and don't have to order so many things. But also we will see some very interesting bugs. So this is kind of thing you have to do in your code. So for the flag synchronization to work, you have to put in mem barrier between the store and the two stores, as well as between the load operation in the shape of the while loop and its test, and the next assignment statement. Also, causal correctness you can make work. So here you have to put in a couple of memory barriers again to tell the hardware where we need to make sure that order is maintained. Here it could sometimes be more complicated than just to drain the store buffer, but it's still a well-known problem how to implement that. There is also yet another programming model called processor consistency you should be aware of, even though it's, to my knowledge, not strictly implemented anywhere. So processor consistency was suggested by Jim Goodman, the guy that first did Snoopy coherence. So what processor consistency says is that all stores performed by one thread should be ordered in program order for everybody else in the system. So that means that flag synchronization works because you write flag and then you write A and then you write flag. That means that the change to A must be seen by everybody before they can see the change to flag. It's not clear whether causal correctness would work. It is not according to the definition Jim Goodman did, but some people have analyzed his work afterwards, say that, well, he probably just forgot to mention it. But if you should be really stringent and clear about what you're implementing, you should say, I'm implementing process consistency with causal correctness in order for you to guarantee that the second case would work. And Dekker's algorithm would not work. So in that respect, it is very similar to TSO. In this lecture, I didn't want you to really get all the details about all the different memory models or exactly how they're implemented. I wanted just to make you a little scared about this tricky subject, and I want you to have respect for how important it is to understand what the memory model is of the underlying system when you write this kind of funky code that I showed you here. There is a tutorial written quite early, just a couple of years after these weaker memory models were defined, by Sarita Adve and Gurush Karakulo, and it's in the papers directory on the course under the course homepage. You should also make sure that you find out what the properties are for the system you're working on, and I should warn you that this is especially important if you work on PowerPC systems. I was once giving a course about memory modeling for PhD students, and there was a person from industry attending that course, and halfway through my lecture he stood up and literally screamed out, "That's the bug, that's the bug." So they have been looking for a bug for months in their PowerPC based system, and it had to do with that they had missed to put in one of those memory barriers somewhere. The memory model of PowerPC is very tricky to understand, and unfortunately I met many people who actually are actively part of implementing PowerPC that agrees with me that pretty much nobody has a full understanding of what's going on there. So tricky stuff. So lastly, something you should think about here after we talked about memory ordering and memory models is what reordering can compilers really do? Can compilers move loads and stores around each other? It sounds like it's a tricky thing. And what does the volatile declaration in C mean? So this is something I'm going to look at the lab, but if I just wave my arms and tell you what the volatile declared variable in C means that two things. It means that it cannot be assigned to a register. It has to be, that value has to be in memory, because it could potentially be a shared variable. And if you put the value of a shared variable in the register and you keep reusing it in the register without reading it out from memory, then you're not going to see any value changes. Another thing, volatile also means that it tells the compiler that this instruction cannot be moved around. Lastly, talk a little bit about x86 and its memory models. So according to themselves, and I have a link to a video at the bottom of this slide, in that video they claim that they implement processor consistency with causal correctness for all non-atomic memory operations. Okay, so that means that loads and stores are implemented with processor consistency with causal correctness. And they say that they implement total store order for all atomic memory operations. Academia don't completely agree with Intel, and academia have studied the matter, and they claim that what is actually implemented in x86-64 these days is actually total store order. I put a link down to Intel's manual for those of you who are interested, and also just for laughs I put that video clip at the bottom from YouTube where you can watch one of the engineers of Intel, very, very smart guy who's been working for years together with very well-known people at Intel to define what memory model they actually are implementing. You can see when he visits Google, and that's another place where there are lots of brilliant people. For example, Kurush Karakulo himself works at Google, people who really understands memory models. So you have all these people in a room, and Intel, they're finally going to tell Google what memory model they implement, and there's a big confusion at this meeting. People just do not understand each other, and I don't think anybody walked away from that meeting with a better understanding of what is being implemented in x86. Often memory models it's hard to discuss about memory models, and also memory models tend to be sort of a religious subject, in the same way that your favorite program language can be a religious subject as well. People have their favorites, and you cannot just solve disagreement by discussing them.